Hello everyone. My name is Chi. I'm very excited to share this presentation with you virtually. If you have any questions or comments, please feel free to send me an email to this address. This talk brings together two different projects that I worked on at Facebook Connectivity previously. In today's talk, I would love to focus more on the latter part, the design of the mechanical steerable arrays, and the fundamental theory underlying and that my colleague Bart and I developed. But before that, I want to also provide a brief overview of the modern satellite constellations and a E-band system demo that we did back in 2017. Since around 2020, we've seen an exponential increase in the number of launched satellites, driven largely by constellations like SpaceX Starlink. This incredible growth in infrastructure of satellites has enabled millions of people to connect high-throughput, low-latency internet access. Designing such constellation requires a careful system engineering, a balance between the space and ground. By launching more satellites in space, the operator can push more aggressive system capacity and revenue. It also benefits with simpler and less expensive terminals on the ground. On the other hand, fewer satellites may require less initial investment, but having more complex and capable terminals required on the ground. In all of these trade-offs, the antenna is truly at the heart of the system design, influencing how we balance the requirements of both space and ground components. The ground terminals serve as the feeder links, prioritize the higher gain and larger aperture antennas for maximum throughput, while the user terminals focus on the lower cost and effective beam steering and beamforming flexibilities. For direct-to-cell, leveraging more advanced antenna design on the space vehicle so that there is no need for modifications in the consumer mobile devices. There are several advantages to use higher frequencies such as V-band or E-band. For feed links, the E-band has a total bandwidth of 15 GHz, which allows for greater system capacity and throughput. Additionally, E-band is lightly licensed compared to other bands, and the atmospheric losses are generally confined to the first few kilometers only, making it ideal for space-to-ground communications. Earlier, we prototyped an E-band system using commercially available components. We demonstrated a system capacity of 40 gigabits per second air-to-ground, and the link is sustainable 10 gigabits per second over a distance 300 kilometers with high link availability. We also ran extensive flight testing and validated the ITU models for rain loss. This is done in Gilliard, a small town nearby Seattle, for a week, confirming the reliability of our system in the real-world scenarios. By carefully selecting and positioning the terminal site locations, it's possible to achieve even higher link availability, potentially reaching 4 nines by using multiple terminals that are spaced far enough apart. For feeder links, where form factor and cost are less critical, we can opt for larger aperture sizes and higher antenna gains, which significantly boost overall system performance and capacity. In general, the Cassegrain parabolic dish antennas are easy to design and manufacture, and we did the implementation of 6-feet E-band antenna with 62 dBi antenna gain. As the aperture size goes up, one needs to pay attention is the surface error, including the surface deflection and roughness. While electronically steerable antennas or ESAs offer incredible flexibilities on beamforming and steering, as well as system benefits like leveraging lower power amplifiers, running spatial power combining. However, our initial design of ESA suffered an extremely high cost due to the limited chip availabilities back then. And each chip can easily cost like tens of dollars, and one array can easily use hundreds or thousands of them. Therefore, we chase for an alternative solution that is mechanical steerable arrays or MSAs. Having the beam steering capabilities with only mechanical rotation, as well as keeping the form factor low profile. Nowadays, kudos to the success of Starlink, ESA have becoming the go-to solution for satellite user terminals. But back then, maybe still valid right now, that we think MSA design is more scalable. One of our design goals was to target at $300 user terminals, making this technology more accessible. One more reason that I found that maybe I need to point it out is the ESA essentially rely on thousands of chips to achieve hundreds of thousands of chips to achieve that essentially boils down to only 2 degrees of freedoms. As an engineer, we can say that there must be some opportunity for optimization. The concept of MSAs is not entirely new. One of the early MSA designs were fixed antenna. It can achieve beam steering capability by the rotation of the radiating aperture in relative to its underlying waveguide. However, it does require more complex waveguide designs to make sure the wave is collimated constructively given the spacing of the radiating slots. Therefore, we introduced additional element level phase control on the radiating aperture or the mask layer. This design approach reduces the need for complex dielectric field or corrugated waveguide design, and instead only using a simple low-cost sheet metals, resulting in more cost-effective and straightforward designs. Here is a simulation of the new MSA beam scanning performance, showing how we can control and steer the beam. And this is the mechanical implementation work done by my colleague Eric Bone, and the whole antenna only using the sheet metals and PCBs and lower the cost. This is the setup of the near field scanning measurement and showing the phase and the amplitude information on the aperture surface at different rotation angle. And here is the far field radiation patterns measured. We also achieved a good X ratio within band and decent gain performance. We can derive the analytical solution for the beam trajectory, and we can see that as the beam steering in the elevation plane, it also introduced additional change in the azimuth plane, which require additional correction to align the desired beam trajectory. It's also worth to know that even though VIX and MSA share the same beam steering mechanism, the trajectory of the beam are different. That makes me wondering why there is a difference between the MSA and the VIX. And Bart and I began to explore other mechanical beam steering methods beyond just rotation, including translation, scaling, twisting, to see what new possibilities MSA could offer. We quickly realized that we need a better understanding of the underlying mechanism and also better mathematical expression of MSAs. So that's why we introduced the concept of Moire patterns. So the Moire patterns often arise in an imaging domain that 2 or more images overlay each other, creating these low frequency components or spatial interferences, which is called Moire pattern. There are many studies on all kinds of Moire patterns in the field that we think it can be leveraged to synthesize and control the dynamics of the beam forming and beam steering. if we can find this, only if we can find this connection to the antenna theory. Therefore, we go back to the fundamentals and look at the definition of directivity. As we all know that the far field pattern is a Fourier transform of the aperture field distribution. And the aperture field then can be decomposed into a source layer and a mask layer with multiplication. We can derive a new steering law that the phase arguments of the source and mask layer must satisfy this simple formula to collimate a plane wave. We can come up this generalized beam steering principle as a few steps. Like firstly, we choose a desired mechanically achievable transformation, like rotation, sliding, shearing, etc. And then we design the feed phase distribution. In order to make sure the antenna to collimate a narrow beam, the phase difference between the source and mask layer needs to be linear regulated. This principle can be applied to any beam steering cases. For example, well-known the leaky wave antennas also follows this linear phase regulation. We can derive the VIX and MSA designs easily using this principle. As we are exploring all kinds of existing Moire patterns, we found this Schuster fringes very interesting. And this Schuster fringes follows this quadratic formula. With only translations, the beam can steer in the elevation plane. This is very interesting and attractive because you can easily implement it with two linear motors. And since they only using the translation, it doesn't have the fast rotation around the keyhole like VIX and MS8 antennas. So here is the sample of showcase of the different mechanical transformations that we were discussing, including the scale, the translation, and also I included other forms of mechanical transformation like shear or twist. Note that I simplified the visualization with only Moire patterns here and ignoring the antenna aperture size. And also this twist mechanism is a little bit exaggerated, but underlying it is using Archimedean spirals. For the non-alpha transformation, for example, we know that a pure band is non-alpha, but still we can, in combination with other type of mechanical transformation, we can still form a beam steering pattern. For non-analytical solution, we can still synthesize the pattern numerically, and there are definitely more opportunities that we can explore in this field. For example, what if we adopt like a few phase shifters, creating a continuous varying patterns instead of mechanical transforming the mask layer? I mean, we can leverage the benefits of ESA but implement it in a Moire pattern way. Then the problem becoming an optimization scenario. In summary, we formulated a generalized mechanical steering principle deriving a novel beam steering law. We explored alternative mechanical steering techniques such as Schuster fringes translation for simpler practical implementation. We developed and validated a low-cost MSC design by integrating element-level phase control into the mask layer. And we also demonstrated an E-band feederlink system showing its capacity and potential for next generation satellite backhaul. That's all the talk, and thank you for your attention.